Hi everyone, Architecture and Operating Systems, and in this video we are going to discuss computer memory systems. In this series of lectures, we learned about computer structure, and we discussed CPU and fetch execute cycle, and we learned about computer structure and the functions of the computer, and also last week we learned about the system bus, and we defined that as network which help communicate between different modules of the computer, as you see here. And I said that the interconnection structure depends on the type of exchanges that these modules have. And we said that we have three main types of exchange. One of them is signal, like read and write. The other one is send and receive the data, so data type exchange. And the last one is the address, as you see here. So the main modules of the computer, they should be able to exchange these three types of communications. So because of that, we have three buses. One of them is called control bus, which consists of control lines. Each line transfer one bit, address bus, and data bus. And they actually connect all these three modules together. And also we learned about the point-to-point interconnection, and we said that to solve a problem with the bus, which is a shared medium, this point-to-point interconnection came to existence, and QPI, invented by the Intel from 2008, is widely used now, which is the multiple direct connection between modules. And the cores, let's say, it works based on protocol, and it doesn't send only a bit of data. Actually use the packet size data transfer, which makes it very more efficient. So this is what we discussed last week, and now we want to discuss about the last module left in the computer structure on the top level, which is the main memory. I'm sure you know about the main memory. Everyone knows what it is, but I have two definitions for that. Computer memory is the area where the computer stores or remembers data. And the other one, memory stores information temporarily or permanently and provides the CPU with its instruction. So we saw in the fetch execute cycle that using the registers, we go to main memory and retrieve data from that and send it to some other part of the machine. So these are the, as you see here, this is the definition of the memory. But we need to know about the key characteristics of memory. What are they? First of all, it's location, where the memories are located. Some of them are internal, those memory that we don't see them, like registers, like main memory and cache. And some are external, like external hard drives, like CDs, DVDs, magnetic disks, floppy disks, if you remember, and tapes, which are very, very old. So we have two types of data in terms of memory, in terms of location, internal and external. The other one is capacity, how we measure the capacity of the memory. One of them is based on the number of the words. If you remember in IS machine, we said that this machine has got 1,000 words. Each word for that machine consists of 40 bits. So that's one way that you can talk about the capacity of the machine, which is not common. The other one is number of the bytes. For example, these days we talk about gigabyte, megabyte, terabyte. This is another way that we can talk about the capacity of the memories. The next one is the unit of transfer, which is important. The number of bits read out or written into memory at a time. So for the main memory, the unit that we have is bits. How many bits is transferred? The other one is word. How many words are transferred on a second? So this is the unit of transfer that we have. And the other one is block. Block is a number of words that are put together as a chunk of data, and we transfer that. So this is easier sometimes, that we discuss that in a few minutes time, that it's easier to send the block of data instead of sending word one by one. So this is the different types of unit of transfer. The other one, another key characteristic of a memory, which is very important, is access time. and access method. So we learn in fetch execute that we need to using memory address register. We need to go to memory and retrieve data, instruction, whatever from the memory. So access to the memory is very important. That's for the main memory, but for different types of memory, again, it is very important. The first one is called sequential access or linear sequence. What is linear sequence is that memory is organized into units of data, as I said, which sometimes they're called records. And we have these records on memory, and in this way of access, it goes line by line into the memory in a linear sequence, line by line. If, you, for example, you want to find a specific word in memory, you've got to go line by line and go to the addresses and reject some of them that you don't need them, and go to the next one to be able to access to the specific word that you are looking for. So because of that, it takes a lot of time, because you've got to scan all the memory till the point that you are looking for that address. For example, if you're looking for a word in for example, address 150, you've got to, it depends on where you start from, but you need to go actually one by one. For example, if you want to start from 100, start from 100, go down line by line, word by word, go down to get to 300, for example. So it takes a lot of time. Tape units, which is very old type of memories, use this type. Direct access, as you see from the name, actually it tries to solve the problem with the sequential access. As with sequential access, direct access involves a shared read memory mechanism, again the same story, but individual blocks or records have a unique address based on a physical location. It means that we put these blocks of data or records on different ports, and each part, each block has got a physical action, a physical address. So if you're looking for a specific word, so you know the unique physical address, first of all you go there, so it's a direct access, but inside that block of data you go for sequential access, line by line to go there. So it's a mixture of linear sequence and having block on the physical memory. So it's first of all you got to find where the block is in the physical actually part, and then it goes based on sequential access. So again, it's not that efficient. It still actually takes a lot of time. The other one, random access, is actually improvement to the last two, and it's actually each addressable location in memory has a unique physically wired-in addressing mechanism. So it means that we can go directly to the point that we are looking for, to the word that we are looking for. The time to access a given location is independent of the sequence of prior accesses and is constant. It means that we know exactly where the word is, and we go direct to that. Because of that, the access time is constant. It doesn't depend on anything. Any location can be selected at a random and directly addressed and accessed. Main memory and some cache systems are random access. So because of that, you know that the RAM is random access memory. That is what it is. So main memory and cache systems, both of them are random access. The other one is called associative access, which cache systems usually use that. It's a bit different with the other ones. This is a random access type of memory that enables one to make a comparison of desired bits locations within a word for a specific match, and to do this for all words simultaneously. Thus, a word is retrieved based on a portion of its content rather than its address. So it works based on the address and similarity with what you're looking for. So when you want to find a specific data, you go and search for the similar ones. So cache works based on that, and it works based on the comparison between the bits in the words and try to retrieve the data from. So these are the four main types of access, which is quite important for you to know the difference between them. Next one is performance of the memory. So definitely access time is the most important because we want to get the data as quick as possible. So access time is very important, and latency, if you have latency, it means that the performance of the memory goes down. For random access memory, this is time it takes to perform a read or write operation. That is the time from the instant that an address is presented to the memory to the instant that the data have been stored or made available for use. Access time for random access method is constant. For non-random access memory, access time is the time it takes to position the read-write mechanism at the desired location. The other one is cycle time. What is memory cycle time? This concept is primarily applied to random access memory and consists of the access time that we discussed before, plus any additional time required before a second access can commence, can start. This additional time may be required for transit to die out on a signal lines or regenerate data if they are read destructively. You need to know that memory cycle time is concerned with the system bus, not the processor. When you're talking about the cycle time, buses are important and the rate of transfer is important as well. And the last one about the performance is the transfer rate. This rate at which data can be transferred into or out of a memory unit. And it's equal with 1 over, for the random access memory, is 1 over cycle time. If you want to compare the performance of the RAM, the memories, so you need to know that if you know that cycle time that we discuss here, 1 over cycle time gives you transfer rate. So this is about the performance. But as I said, the most important is access time. Physical type of the memory. We've got 4 main types of physical type: semiconductors, magnetic, optical, and magneto-optical. Because this is not the scope of our work, it's good to know them, but if you're interested, you can actually Google it, search for actually how the physical aspects of the memory are. And physical characteristics, which is very important, we've got 2 important definitions here. One of them is volatile and non-volatile. Volatile, in a volatile memory, information decays naturally or is lost when electrical power is switched off. When electricity goes, it goes. All the data will go. In a non-volatile memory, information once recorded remains without deterioration until deliberately changed. No electrical power is needed to retain information. So this is very important. So if you want to actually save data permanently, so you need to save that on a non-volatile, for example, hard drive. And RAM is important here because we need to have some data, some information stored on the computer that it shouldn't be erasable and it shouldn't be volatile. It means that when the power goes, we should still have them on the machine. So they should be volatile and non-erasable. ROM is that type of memory that we have. So we've got erasable and non-erasable type of memories that some of them you cannot, in some memories you cannot erase the information like ROM that we said. So that was the different types of memory that we discussed. But how to use them, how to design a memory for a machine. In terms of the memory design, 3 important questions are how much, what is the capacity? How fast is that? So what access time and how much does it cost for us? These are the main issues that we need to think about in memory design that we'll discuss later on about the hierarchy of the memory. So here we've got 3 points: capacity, access time, and the cost. We need to consider these 3 factors if we want to talk about the memory always. So there are 3 important relationships between these 3 factors. When you have greater capacity, definitely the cost will go down. If you go for greater capacity, cost per unit of memory will go down. If you have greater capacity, it will be slower because again, access time will increases if you have a bigger memory. And if you want to have a faster access time, very quick, it will be very expensive. So these are 3 important equations that we need to consider in memory: greater capacity, smaller cost; greater capacity, slower access time; faster access time, greater cost. How to design them? How to design a memory system? We need to combine all of them, combine all these: speed, capacity, and the cost. So because of that, the pyramid of memory actually comes to discuss. What's that? On one side, we've got the memory, as you see, inboard, outboard, and offline. Decreasing cost per unit when we go down. If we go down, the cost will go down. It means that the most expensive memory that we have is register. Because of that, registers, in terms of the number of the memory that we have, is way less than, for example, main memory, less than cache, because it's very expensive. So when you go down, it's getting cheaper. For example, external hard drive is the offline storage, is way cheaper than about a single unit of memory than registers. So when you go down, the price go down. Capacity, the register, we are talking about the number of the words, a block or a couple of blocks of registers, a couple of words of register. But here we talk about terabyte of data, of capacity bits, terabyte of bytes. So the capacity increases here. The other one, access time. It takes registers are very quick, very fast, and the access time is quite low. But here, the access time here is very high. So when you go down, the access time increases. So register is the fastest, then cache, then main memory, then magnetic disk, CD, DVD, and hard drive, HDD, and the other one is actually external hard drives. So this is how the access time increases in memory. The decreasing frequency of access of the memory by the processor. So we know that the processor needs this information, instruction, data, whatever. So this is the frequency. As you learn in the fetch execute, we've got to use always registers should be used. So this is the highest frequency that we use. The registers are widely used by the CPU. Less cache, less main memory, less hard drives and CDs and external hard drives if you want. So this is the way. Actually, when you go down, it shows the decreasing frequency of accessing of the memory by a processor. So what should be done? This hierarchy helps us to design a memory system. The memory that we discuss in the computer architecture should consist of all of them. Smaller, more expensive and faster memories, smaller, expensive, fast, should be combined or supplemented by larger, cheaper, and slower memories. So because of that, in machine, we've got all of them. But if you want a faster machine, high performance machine, you need to pay more because you have more of these. You've got a full cache, for example. You've got a half cache, it depends. But this combination, but a good combination will make a good machine and faster machine for you. So this is the hierarchy of the memories, and we need to know all these stuff. The last thing that we've got to know is cache memory. What is cache memory? Because main memory we know and we learn about that. Registers, we discussed that, how they work. But here, only cache left. What is cache? Cache, the concept of cache is the combination of fast and expensive memory with less expensive and lower speed. It means that cache is a buffer between these two. This is cheaper, this is expensive, cache is between them. This is faster, this is slower, this is between them. So as you see, cache is between register and, or let's say CPU and the main memory. Cache contains a copier portion of the memory. What happens is that, let me come here. Cache, what it does, it tries to bring a block of data to the to contain the block of data instead of the word. Let me give an example. For example, a CPU wants an instruction which is located in 300. Remember the fetch execute cycle. So what happens in the without the machine without cache, the CPU should be using the register, should go to the memory and brings the 300 to the CPU. So next one, 301, 302, 304. So as you see, it takes a lot of time for the CPU to go and use all the buses and so on to actually bring the instruction to the memory. What cache does, cache is faster than memory. What it does, it says that, okay, if you're looking for 300, the location 300, I will go and bring from 300 to 350, for example. It brings a block of data and put it here in the cache. And CPU for the next one goes and checks the cache memory. If CPU could find the word, the address inside the cache, it doesn't need to go to main memory. So the access will go down. And here, the link between the CPU and cache is way faster. So instead of going to the main memory, which is slower than that, but because you copied a portion of the main memory and put in the cache, each time the CPU accesses the cache and gets whatever it needs, which is way faster. Here, it's a block transfer that we transfer a block of data to the cache, but here we actually the CPU use word by word. It's a word transfer. So as you see, we've got word transfer here. Here we have block transfer. There you go. For example, if you are looking for, if the CPU wants a word in location 2, what cache does, cache brings from 0 till, for example, a block of that, the keywords. A block of that will sit in the cache memory, and the CPU, instead of going to the main memory for the next instruction, it will go to the cache. So the concept of cache is to bring the block of data to hold the block of data, and helps the CPU to run faster instead of going to the main memory each time. So for high performance machines, we've got different levels of cache. This is main memory, this is CPU. You can have block of them. It means that if you're looking, for example, for location 200, level 3 brings between 1 till 500. Level 2 brings a portion of that here. Level 1 brings another portion of that. So by this one, actually, you cut a lot of transmission between the a number of the transmission between main memory and CPU, and you will increase the efficiency of the machine. So this is the end of the discussion on the memory systems, and this is the last lecture in terms of the CPU and the computer structure. Thank you very much.